Let's begin with the first of four problems that involve the entropy change that takes place during a process. Air in a piston cylinder assembly undergoes a process from state 1, where T1 equals 300 K and P1 is 100 kilopascals, to state 2, where T2 is 500 K and P2 is 650 kilopascals. Using the ideal gas model for air, determine the change in specific entropy between these states in kilojoules per kilogram K. If the process occurs A, without internal irreversibilities, or B, with internal irreversibilities. So let's get this A-B question out of the way. Entropy is a property. It's just like specific volume or internal energy or enthalpy. It's a property that you can look up in a table. So it's not dependent on the path to a state. Otherwise, we couldn't put the values in a table. So delta S is the same for reversible or irreversible processes. Let's lay out a storyboard for this problem. We have a schematic with a piston cylinder assembly filled with air. And we're going to take the air, all the molecules of the air, as the boundary of our system. And here's what we're given. Initial temperature is 300 K, and the initial pressure is 100 kilopascals, which is 1 bar. And state 2 has a temperature of 500 K and a pressure of 650 kilopascals, which is 6.5 bar. And we're going to treat this as a closed system. We'll ignore any changes in kinetic or potential energy as being completely insignificant. And we're going to treat the air as an ideal gas. And we want to find the change in entropy between these two states. So we're going to use the air table. The air table is for air as an ideal gas. And we introduced this equation in previous problems, that the change in entropy, or in this case, the change in specific entropy for a process, is this S naught of T2, that's minus S naught of T1, where this S naught is a value found in the air table. And then that minus R times the natural log of P2 over P1. So in the air table at 500 degrees Kelvin, we'll get S naught of T2, which is 2.21952 kilojoules per kilogram K. And S naught of T1 would be S naught of 300 K, and we get a value for that. So now we can substitute and solve. We have delta S is S naught of T2, our first value here, minus S naught of T1, the second value here that we got from the air table, minus the gas constant R, which is the universal constant in SI units, 8.314, divided by the molecular weight of air, which is 28.97, and that quotient having units of kilojoules per kilogram K, and then times the natural log of P2 over P1. And that gives us a change in entropy of minus 0.0197 kilojoules per kilogram K. So let's plot this on a TS diagram. Our temperature scale, we have 300 K and 500 K. And our pressure lines, we have 1 bar here. And above that, we have 6.5 bar. And so state 1 exists at 300 K and 1 bar. And state 2 exists at 500 K and 6.5 bar. And notice that the delta S is negative. That means that S2 has a value that is less than S1, as I've drawn it here. Notice also that the first part of this delta S equation, which, S naught of T2 minus S naught of T1, notice that that gives us a positive value. So that's trying to create an entropy change that's positive. But then we subtract from that a term here, which is a function of pressures. And that tends to decrease, in this case, that tends to decrease delta S. And the pressure seems to have more effect here than the temperature. And that's why we get a value that is negative.